Hello dear students, all of you welcome to Vidyana classes. Today we will discuss invertible matrices. Definition of invertible matrices. If capital A and capital B are two square matrices of same order satisfying AB is equal to BA is equal to unit matrix I. The unit matrix I of same order as A or B. A and B are two square matrices of same order satisfying AB is equal to BA is equal to I. The unit matrix that is I of same order as A or B, then capital then capital B is equal to multiplicative inverse of A. Denoted by A inverse. Then B is equal to the multiplicative inverse of A denoted by A inverse. Also, A is equal to also A is equal to multiplicative inverse or simple inverse of B, written as B inverse. If capital A and capital B are two square matrices of same order satisfying AB is equal to BA is equal to I means unit matrix. The unit matrix I of same order as A and B, that means A, B and I have the same order. Then B is called the multiplicative inverse of A denoted by A inverse. Also A is equal to the multiplicative inverse or simple inverse of B written as B inverse. B to the minus 1 is read as B inverse. From the above definition, it is clear that A and B are invertible. That means inverse of A and B are exist. From the above definition, it is clear that A and B are inverse to each other. If first condition, capital A, capital B and unit matrix I are of same order. A, B and I are of same order. That means order of A is equal to order of B is equal to order of I. Second condition, AB is equal to BA is equal to I. These two conditions implies as B is equal to A inverse and A is equal to B inverse. If these two conditions are satisfied, then we say that A inverse is equal to B and B inverse is equal to A. Clear? These are two necessary conditions so that the inverse of A and B are exist. Example, let capital A is a matrix having elements 2, 5, 1 and 3. Its order is 2. Capital B is a matrix 3, -5, -1 and 2. Let capital A is a matrix having elements 2, 5, 1, 3 and capital B is the matrix having elements 3, -5, -1 and 2. It is also a square matrix of order 2. Clear? Both have the same order. AB 2, 5, 1, 3, 3, -5, -1, 2. Matrix multiplication is possible if column of first is equal to row of second. 2, 2, 2, 2, 2, 2. Column of first is equal to row of second. So the multiplication is defined. According to the rule of matrix multiplication, go through row 1, come down in column 1, multiply the corresponding elements and add them. 2 into 3 that is equal to 6, 5 into -1 that is -5. Next, go through row 1, come down in column 2, multiply the corresponding elements and add them. That is 2 into -5 that is -10, 5 into 2 that is equal to 10. Next, go through row 2, come down in column 1, it gives 1 into 3 that is equal to 3, 3 into -1 equal to -3. Next, go through row 2, come down in column 2, multiply the corresponding elements and add them. 1 into -5 that is -5, 3 into 2 that is equal to 6, which is same as 1, 0, 0, 1 is a unit matrix of order 2. I or I2. I2 means unity matrix having order 2. It is a 2 cross 2 matrix. Its order is 2. BA B contains 3, minus 5, minus 1, 2. A contains 2, 5, 1 and 3. According to the matrix multiplication rule, we have 3 into 2 that is equal to 6, 5, minus 5 into 1 minus 5, 3 into 5 that is 15, minus 5 into 3 that is equal to minus 15, minus 1 into 2 that is equal to minus 2, 2 into 1 that is equal to 2, minus 1 into 5 that is minus 5, 2 into 3 that is equal to 6, which is same as 1, 0, 0 and 1. It is also a matrix of order 2. 2 cross 2, which is same as I or written as I2. It satisfies all the conditions so that the matrix will be invertible. That means the inverse is exist. Since order of A is equal to order of B is equal to order of unit matrix I, each is equal to 2. Order of A is 2, order of B is 2, order of I is also 2. The first condition is satisfied. AB, it is the second condition. It is since order of A is equal to order of B is equal to order of I is equal to, and the second condition AB is equal to BA is equal to I of order 2 implies this. These two conditions are satisfied. A inverse and B inverse are exist. A inverse and B inverse are exist. That is, B is equal to A inverse and A is equal to B inverse. Clear? If these two conditions are satisfied, then the inverse A is inverse to B and B is inverse of A. Clear? Okay. Note a matrix whose inverse is exist is called a matrix whose inverse is exist is called invertible matrix. Here A and B are invertible matrices. Since the inverse of A is B and inverse of B is A matrix whose inverse is exist is called invertible matrix. Next note, a rectangular matrix has no inverse. A rectangular matrix has no inverse. For example, a rectangular matrix has no inverse. Example, let A is a matrix having elements 1, 2, 3, 2, 3, 5. It is a matrix of order 2 cross 3. B is a matrix having elements 1, 3, 5, 4, 2, 1. It is a matrix of 3 cross 2. A and B has no inverse. Since A and B has no inverse, since A and B and B have no inverse. As A, B are not square matrices. The first condition is not satisfied. A, B and I are same order. Here A and B have no inverse. As A and B are not square matrices, that means the first condition is not satisfied. It is the first condition. Also, AB two to three, 3 to 2. AB, the order of AB is 2 cross 2, and the order of BA 3 to 2, 2 to 3, that is 3 cross 3. Both AB and BA are defined. Both AB and BA are defined, but AB is not equal to BA. The second condition also not satisfied. Since order of AB is 2 to 3, 3 to 2, the order of AB is 2 cross 2. Is 2. Order of AB is 2. Since it is a square matrix, and order of BA is 3. BA means it is the order of 3 cross 2, it is the order of 2 cross 3 to 2, 2 to 3. Order of BA is 3 cross 3, that means 3. A matrix whose inverse exists is called invertible matrix. A rectangular matrix has no inverse. For example, A and B are two rectangular matrices. A and B have no inverse. As A and B are not square matrices, that means the first condition is not satisfied. Here both AB and BA are defined, but A not equal to BA. So order of AB Here order of AB is equal to order of BA is equal to 3, so AB not equal to BA. Clear? Clear? Okay. Uniqueness of inverse. It is a theorem. Inverse of a square matrix, if it exists, is unique. Inverse of a square matrix, if it exists, is unique. It means inverse of a square matrix is unique. That means a square matrix has one and only one inverse. It has no second inverse. Proof, let capital A is equal to square bracket Aij be a square matrix of order n. Let capital A be a square matrix of order n. A has only one and only one inverse. If there exist two inverses, that they will be equal. If possible, let capital B and capital C are two inverses of capital A. If possible, let B and C are two inverses of A. We have to show, to prove the uniqueness. It is sufficient. It is sufficient to show, to prove the uniqueness. It is sufficient to show B is equal to C. Uniqueness. To prove the uniqueness, it is sufficient to show B is equal to C. Now, since B the inverse of A implies AB is equal to BA is equal to I. Again, C is the inverse of A implies AC is equal to CA is equal to I. To prove B is equal to C. Now, B is the same as B into I. Since BI is the same as IB is equal to B, which is same as B I is equal to SC. Since I is equal to SC, which is same as BA, into C. Since matrix product is associative, which is same as B is equal to I into C. Since B is equal to I, B is equal to implies B is equal to IC, which is same as C. Since IC is equal to CI is equal to C, therefore B is equal to C. Hence, the theorem is proved. Inverse of a square matrix is unique. Inverse of a square matrix which is exist is unique. Suppose A is a square matrix, it has two inverses as B and C. To prove the uniqueness, it is sufficient to show B is equal to C. Since B is the inverse of A, AB is equal to B is equal to I. Since C is the inverse of A, AC is equal to CA is equal to I. Now B is equal to BI. I can be written as AC. I is equal to AC by the matrix which is same as BAC. Since matrix product is associative, BA is equal to I, so it is B is equal to IC. IC is same as C. Since IC is equal to CI is equal to C, therefore B is equal to C. Hence the theorem is proved. That means every square matrix has one and only one inverse. If there exist two inverses, then they will be equal. Clear? Clear? Okay, write down. Next theorem, if capital A and capital B are invertible matrices of the same order, then inverse of AB is equal to B inverse into A inverse. Let capital A and B are two invertible matrices of same order. Implies since A and B are invertible matrices, implies A inverse and B inverse are exist. Both AB and B inverse, A inverse are defined. Also, order of AB is equal to order of B inverse, A inverse. Since A and B are two invertible matrices of the same order, implies A inverse and B inverse are exist. Both AB and B inverse A inverse are defined. Also, order of AB is equal to order of B inverse into A inverse. To show AB inverse is equal to B inverse into A inverse. It is sufficient to show AB into B inverse A inverse is equal to I. I is the unity matrix. Since if X inverse is equal to Y, then X into Y is equal to Y. If X inverse is equal to Y, then X into Y is equal to unit matrix, where X and Y are two square matrices. Clear? Now we have to show AB inverse is equal to B inverse into A inverse. Here X is AB and Y is equal to B inverse into A inverse. To prove AB inverse is equal to B inverse into A inverse, it is sufficient to show AB into B inverse into A inverse is equal to I is the unity matrix. Now AB into B inverse into A inverse, which is same as AB into B inverse into A inverse. Since matrix product is associative, that is AB into C is equal to A into BC. It is taken as A, it is BC, which gives AB into C. Which implies A into AB into B inverse A inverse, which is equal to A B inverse whole into A inverse. ABC is same as ABC, since matrix product is associative, which is same as A into I into A inverse. Since B into B inverse is equal to I, which is same as into A inverse. Since AI is equal to A, which is same as I. Since A into A inverse is equal to I, implies AB into B inverse A inverse is equal to I. It is taken as X, it is Y, XY is equal to I, that implies X inverse is equal to Y. X inverse is equal to Y, then XY is equal to I. Here AB into B inverse A inverse is equal to I implies AB inverse is equal to B inverse into A inverse. Hence, the theorem is proved. Clear? We have to show AB inverse is equal to B inverse into A inverse. It is sufficient to show AB into B inverse into A inverse is equal to I. Now AB into B inverse A inverse, which is same as AB B inverse whole bracket A inverse. It is taken as A, it is B and C, which is same as AB into C. Since matrix product is associative, which implies AB into B inverse A inverse, which is same as ABC is written as ABC. C means B inverse. Since matrix product is associative, whole into A inverse. B into B inverse is equal to I. So we can write A into I into A inverse. AI is equal to A. So it gives A into A inverse. A into A inverse is equal to I, which implies AB into B inverse A inverse is equal to I implies AB inverse is equal to B inverse into A inverse. Hence the theorem is proved. Clear? Clear? Okay. Next, elements of mathematics, exercise 4B, page number 116. So that the given matrix is its own inverse. Prove. Let capital A be the given matrix. To show A inverse is equal to A. It is taken as A, so that the A is its own inverse. That means to show A inverse is equal to A. It is sufficient. It is sufficient to show A inverse is equal to A. That means A is equal to I. To prove, since AB is equal to BA, is equal to I implies B is equal to A inverse and A is equal to B inverse. To show A inverse is equal to A, that means A into A is equal to the unit matrix. It is sufficient to show A into A is equal to unit matrix. A into A is equal to 0, 1, 1, 0 into 0, 1, 1, 0. We have to show A into A is equal to unit matrix. By the multiplication rule, go through row 1, come down in column 1, multiply the corresponding elements and add them, which gives 0 into 0, that is equal to 0, 1 into 1, that is equal to 1, 0 into 1, that is equal to 0, 1 into 0, that is equal to 0. Next, go through row 2, come down in column 1, it gives 1 into 0, that is 0, 0 into 1, that is equal to 0. Next, go through row 2, come down in column 2, multiply the corresponding elements and add them. 1 into 1, that is equal to 1, 0 into 0, which is equal to 0, which is equal to that, which is same as 1, 0, 0 and 1. It is the unit matrix of order 2, which implies this A into A is equal to I, which implies this A inverse is equal to A. Therefore, the statement is proved that the given statement is true. To show the inverse of this matrix is itself, so that matrix having elements 0, 1, 1, 0 is its own inverse. Let A is equal to this matrix to show inverse of A is itself. It is sufficient to show A is equal to I, since by the definition we have AB is equal to BA is equal to I implies B is equal to A inverse. AB is equal to B inverse. A is given by 0, 1, 1, 0. By the multiplication rule, it gives the unit matrix, which implies this A into A is equal to I. That means A inverse is equal to A. Since AB is equal to I, B is equal to A inverse. That is, here A is A, B is also A. So A inverse is equal to A. Therefore, the given statement is proved that true. Clear? Okay. Write down. Next, elements of mathematics, exercise 4B, page number 116, question number 7. If A is a square matrix of order 3, having elements 0, 1, minus 1, 4, minus 3, 4, 3, minus 3, 4, then show that A is an involuntary matrix and hence A is equal to A inverse. Capital A is an involuntary matrix. What is involuntary matrix? Note, a square matrix capital A is said to be is said to be involuntary if A square is equal to I, where I the unit matrix same order as A, where order of A is equal to order of I. A square matrix capital A is said to be involuntary if A square is equal to Y, where order of A is the same as order of I. In question number 7, we have to show A is an involuntary matrix and hence A is equal to A inverse. To show A is an involuntary matrix, which implies and implies by. It is the first case to show A is an involuntary matrix, which implies and implies by A square is equal to I. The matrix capital A is said to be involuntary if A square is equal to I, where the order of I is the same as order of A. Second, A square is equal to I implies A is equal to A inverse. There are two cases in question number 7. Proof of I. First bit. To show A square is equal to I. A square which is same as A into A, which is same as A is given by 0, 1, minus 1, 4, minus 3, 4, 3, minus 3 and 4. Into 0, 1, minus 1, 4, minus 3, 4, 3, minus 3 and 4. A is given by 0, 1, minus 1, 4, minus 3, 4, 3, minus 3 and 4. 0, 1, minus 1, 4, minus 3, 4, 3, minus 3, 4. By the multiplication rule, go through row 1, come down in column 1, multiply the corresponding elements and add them. It gives 0 into 0 that is equal to 0, 1 into 4 that is equal to 4, minus 1 into 3 that is equal to minus 3. Next, go through row 1, come down in column 2 and multiply the corresponding elements and add them. 0 into 1 that is equal to 0, 1 into minus 3 that is minus 3, minus 1 into minus 3 that is equal to plus 3. Next, go through row 1, come down in column 3, multiply the corresponding elements and add them. 0 into minus 1 that is equal to 0, 1 into 4 that is equal to 4, minus 1 into 4 that is equal to minus 4. Next, go through row 2, come down in column 1, multiply the corresponding elements and add them. 4 into 0 that is equal to 0, minus 3 into 4 that is minus 12, 4 into 3 that is equal to 12. Next, go through row 2 and come down in column 2, multiply the corresponding elements and add them. 4 into 1 that is equal to 4, minus 3 into minus 3 that is equal to 9, 4 into minus 3 that is minus 12. Next, go through row 2, come down in column 3, multiply the corresponding elements and add them. 4 into minus 1 that is minus 4, minus 3 into 4 that is equal to 4 into minus 1 that is minus 4, minus 3 into 4 that is minus 12. Minus 12, 4 into 4 that is equal to 16. Next, go through row 3, come down in column 1, column 2 and column 3 that is which gives 3 into 0 that is equal to 0, minus 3 into 4 that is equal to minus 12, 4 into 3 that is equal to 12, 3 into 1 that is equal to 3, minus 3 into minus 3 that is 9, 3 into 3 that is equal to 3, minus 3 into minus 3 that is equal to 9, 4 into minus 3 that is equal to minus 12. Next, 3 into minus 1 that is minus 3, 3 into minus 3 that is minus 3, minus 3 into 4 that is equal to 12, minus 12, minus 12, 3 into minus 1 that is minus 3, minus 3 into 4 that is equal to minus 12, 4 into 4 that is equal to plus 16, which gives, which is equal to, it is 1, it is 0, it is 0, it is 0, it is 1 and it is 0, 0, 0 and 1, which is equal to I, which is same as I3. A is a matrix of order 3, I is also a matrix of order 3. Since order of A is equal to order of I. So, first part is proved. Implies this A square is equal to I. Therefore, A is an involuntary matrix. So, case 1 is proved. Case 2, second part. We have A square is equal to I, which implies A into A is equal to I. Since A A square is the same as A into A, which implies A is equal to A inverse. Since AB is equal to BA is equal to I, implies A inverse is equal to B and B inverse is equal to A into A is equal to I, that implies A is equal to A inverse. Since AB is equal to I, A inverse is equal to B. So you can, it is A, it is B. B is equal to A inverse. Hence proved. Hence second bit is proved. In case 1, we have proved A square is equal to A square is equal to I, A square can be written as A into A, which is same as I. A is equal to I, A is equal to A inverse. Since AB is equal to I, that implies A inverse is equal to B. B inverse is also A. It is A, it is B, B is equal to A inverse. So the second part is proved. Clear? Are you clear? Okay. Write down.